Hello everyone, this is D. Chinnagokari. So in this video lecture, I am going to discuss about the electronic configuration. So here, what is the electronic configuration? Electronic configuration is nothing but the systematic arrangement, the systematic arrangement of electrons, the systematic arrangement of electrons in the atom is called what? Electronic configuration. So here we use two methods to write the electronic configuration, that is orbital method and NLX method. So here NLX method is very important to write the electronic configuration. So in NLX method, so here n is the principal quantum number. So in last video, what is the principal quantum number? I explained principal quantum number, and L is the azimuthal quantum number or subcell quantum number, azimuthal quantum number. This also, the about quantum numbers I have explained in the last video, and X is the number of electrons in subshell, number of electrons in the subshell. So here this is the method here we are going to use to write the electronic configuration. So when you want to write this electronic configuration very systematically, we should follow some rules. So what are the rules? The first one is above principle. So we should follow these three rules. The first one is above principle. So what is above principle? So according to above principle, here above means building up. So building up. So here according to above principle, so where we need to fill, this gives information about how to fill the electrons in different energy levels. It gives, so according to above rule, so first we should fill electrons, in the lowest energy level, in all available energy levels, that is called above rule, or simply, so electrons must be filled in the increasing order of their energy levels, or electrons must be filled by the increasing order of energy level. So how to select the increasing order of energy level? So here, which is how to select which is having lowest energy, means how to say which subcell is having the lowest energy level. So we select the how we select the lowest energy level. So the energy level which is having lowest n plus L value, is the lowest energy level. So First we need to see their n plus l value. For example, 1s, 2s, 3s, like that these are available. 1s, 2s, 3s, 2p, 3s, like that these are available, in which among these which is having the lowest energy level. How we can say which is having the lowest energy level? So we will see the n plus l value. So here what is the n value? This is the principal quantum number we already know in NLX method, that is n value, that is 1 plus s is the subcell quantum number we already know. Here s is equal to means s l value is 0. So we already know, that is, so again I am revising here, L equal to 0, that is S subcell, 1 P subcell, 2 D subcell, 3 F subcell, and so on. Okay. So here principal quantum number n plus L value 1 plus 0, that is equal to 1. So here 2 plus 0, that is equal to 2. Here 2 plus 1, that is equal to 3. Here 3 plus 0, that is equal to 3. Now we are having the n plus L values. So among all these, which is having the lowest n plus L value, that is 1s. 1s is less than 2s. Then after, when you see the 2p and 3s, which are having the same n plus L value, if condition, if same n plus L value, same n plus L value, then how to select the lowest energy level? Means then we need to see the lowest n value. So which is having the lowest n value, that is only having the lowest energy, which means first we need to see the n plus L value there, which is having the lowest n plus L value, that is only the lowest energy. If any two subcells are having, any two energy levels are having the same n plus L value, then we need to see the lowest n value. So here among these 2p and 3s, 2p is having the lowest n value, so that 2p is less than 3s. So in this order we need to fill the electrons. Okay, this is according to Abbo rule, which means Abbo rule says that how to fill the electrons in different energy levels. So we need to fill the electrons in different energy levels in the increasing order of their energy. So how to select the energy, means how to know their energy? By using the n plus L value and n value. First of all we should check the n plus L value. So which is having the lowest n plus L value, that is only the lowest energy. If any two subcells are having the same n plus L value, then we need to see the lowest n value. In this way we can select the lowest energy level, so that we can fill the electrons in different energy levels. So here based on this Abbo rule, we are having one chart, that is also called Moiler chart. So by using this Moiler chart, we can arrange the increasing order of the energy of different subcells. We can know the energy of different subcells without any confusion. So here this Moiler chart contains n values and L values. So here n values we already know they are starts with the 1, 2, 3, 4, 5, 6, 7, 8, up to 8 we are taking. And L values we already know, L values are start 0, 1, 2, 3. Likewise L values are there. So we already know L equal to 0 means that is S subcell which is present in the first cell. So we write 1s. So which means 1s means S subcell present in the first cell. Next 2s, which means S subcell present in the second cell. 3s, S subcell present in the third cell. So we already know S subcell present in each and every cell. Likewise we are writing 4s, 5s, 6s, 7s, 8s. Next L equal to 0, L equal to 1, n equal to 1 means first cell does not contain any p subcell. P subcell starts with the second cell, that's why we are writing 2p, 3p, 4p, 5p, 6p, 7p. Up to 7p is enough. So here why we are not writing 1p means first cell does not contain any p subcell, and why we are not writing say 8p. So up to 7p only is enough for us to fill the all to write the electronic configuration of all elements. Next, coming to the L equal to 2, L equal to 2 means D subcell. We already know D subcell starts with the third cell, that is 3D, 4D, 5D, 6D. Up to 6D is enough. 7D is also present, but 7D is not required for us to write the electronic configuration of all elements. Up to 6D is enough for us to write the electronic configuration of all elements. Next, L equal to 3. L equal to 3 means F subcell. F subcell starts with the fourth cell. So first cell 4F, 5F. First cell, second cell, third cell does not contain any F subcell. Okay. So next step is drawing arrow marks. Drawing arrow marks. Here, so like this, you draw arrow marks. You divide into set of arrows. First two set of arrows should contain only one subcell. Next, second set of two arrows contain two subcells. Next, third set of two arrows contain three subcells. Next, fourth set of two arrows contain four subcells. Likewise. So this is the molar chart, and next then after write the increasing order of the energy of subcells. So first 1s is less than, then after you should come again here tail position of the next arrow. What is the tail position of the next arrow? You will get, that is 2s. So now this arrow is completed, and again you should come to the tail position, not from the head position. Tail position only we should come. From this back side only we should come. So after completion of 2s, next third arrow contain 2p after 3s. This arrow is finished. So again you should come from the tail position itself. Means 3s after 3p is less than, then after 4s is less than. So now this arrow is finished. Next come to the 3d is less than, 3d after 4p after 5s. Likewise, and so on. This is the increasing order of subshells. So in this order only we need to fill the electrons. Yes. Next, another rule, that is Hund's rule. Next we are having Hund's rule. So what is Hund's rule? So here Hund's rule says that Hund's rule gives information about degenerate orbitals. So what are the degenerate orbitals means here, children? Degenerate orbitals means the orbitals which are having the same energy. The orbitals which are having same energy is called degenerate orbitals. So means they are having same n plus l value and same n value, so that we cannot say which one is having high energy, which is having low energy, so that we consider they are having same energy, so such type of orbitals are called degenerate orbitals. For example, 2p is there, so we already know p subcell contain 3 orbitals, so that is px, py and pz. So these are the 3 orbitals present in the 2p subcell. So here for each and every orbital we will get 2 plus 1, that is equal to 3, n plus l value 3 and n value is equal to 2, n plus l value 3 and n value is equal to 2, so that we cannot decide which is having high energy, we cannot decide which is having high energy and low energy, so that what we can consider, all they are having the same energy. Such type of orbitals are called degenerate orbitals. So in the degenerate orbitals, how to fill the electrons? In the degenerate orbitals, we need to fill the electron 1 electron only, up to all they are having 1 electron only. After having 1 electron only, we should start pairing, and also while filling the electron they must have the same orientation. For example, here 3 electrons are available, so we are filling in the 2p, so we need to fill 1 2 3, like that only we need to fill. This is the correct electronic configuration. But if you fill like this, even though they are contain 1 electron also, they are not have the same spin, means they should have the same spin, and each degenerate orbital must have 1 electron only. Then after only we should start pairing. Means how to define this Hund's rule here? Hund's rule says that, so in degenerate orbitals, after filling 1 electron with the same spin only, we need to start pairing. That is the Hund's rule. Okay. So for example, nitrogen is there. Nitrogen atomic number 7, its electronic configuration is 1s2, 2s2, 2p3. So here in 2p3, so how we need to fill the electrons? That is 1 2 3. This is only the correct electronic configuration. This is the px, py, pz. So -1 0 plus 1 magnetic quantum numbers also. This is only the correct electronic configuration. Next, if you feel like this, this is the wrong electronic configuration. It is not following the Hund's rule, it is following the Hund's rule. Next, coming to the fourth rule, that is Pauli exclusion principle. Pauli exclusion principle. So Pauli exclusion principle says that no 2 electrons are having the 4 quantum numbers equal. So what Pauli exclusion principle says that no 2 electrons are have the same or have the 4 quantum numbers same, at least one quantum number must be different. For example, when you take the helium, we take the helium, because helium contains 2 electrons. Okay, its electronic configuration is 1s2. So when you write the electronic configuration 1s2, so this is the s subcell. S subcell contain 1 orbital, one is upward direction, another one is downward direction. When you see the 4 quantum numbers here, principal quantum number is 1, azimuthal quantum number is 0, magnetic quantum number is also equal to 0 for this electron, and spin quantum number s is equal to plus of. Why? Because it is in the upward direction. And when you see for this, n is equal to 1, l equal to 0, m also equal to 0, s is equal to minus of. Why? Because it is in the downward direction, which means even though we are taking the electrons present in the same cell and same subcell, and one is having 1 principal quantum number 1, azimuthal quantum number 0, magnetic quantum number 0, spin quantum number is plus of, and another one is having same principal quantum number, same azimuthal quantum number, same magnetic quantum number, but spin quantum number is different. So this Pauli exclusion principle, according to this Pauli exclusion principle, so an orbital can accommodate only 2 electrons. One is the upward direction, another one is the downward direction. So this is about these three rules. These 3 rules only we are going to use to write the electronic configuration. Okay. So first above rule says that we should fill electron in the increasing order of their energy. Hund's rule says that in degenerate orbitals we should fill 1 electron in the degenerate orbital. Only after filling of 1 electron in degenerate orbital with the same spin only we should start pairing. And Pauli exclusion principle says that so no 2 electrons are have the 4 quantum numbers same. So this is about the 3 rules and Euler chart. And next some exceptional electronic configurations, that is copper and chromium. So here what is that exceptional electronic configuration? Remaining electronic configurations everyone can write, but this copper, when you see copper and chromium, these are having exceptional electronic configuration. So what are the exceptional electronic configurations here? So when you follow the all rules, chromium atomic number is 24, its electronic configuration AR 3D 5 4s 1. So here when you see this electronic configuration, here in between 3D and 4s, 4s is having n plus l value, that is equal to 4, 3D is having n plus l value, that is equal to 5. So here 4s is having the lowest n plus l value, but where we are filling the electron in 3D. Okay. First, without completely filling the electrons in the 4s, we are filling the 3D. So why it is? Because so when you fill these electrons likewise here, it will get some extra stability, that is half filled electronic configuration, some symmetry is there, and this here electrons can exchange with one another. When they are exchanging with one another, they are going to lose their energy, so that they get some extra stability. This is called what? Exchange energy. Exchange energy. Exchange energy. Due to exchange energy, it is having such type of electronic configuration. Okay. And here number of exchanges is equal to summation of n minus 1, where n is the number of unpaired electrons. N is equal to number of unpaired electrons with the same spin, So here, so number of exchanges 5 minus 1. Why? Because here 5 electrons are there with the same spin. So summation of 4 you will get. So summation of 4, how we write? That is 4 plus 3 plus 2 plus 1, that is totally 10 exchanges. 10 exchanges are possible. So for copper also we are writing 3d10 4s1. Its atomic number is 29. So AR 3d10 4s1. Why? Because here also we are getting one exceptional electronic configuration, that is stable electronic configuration, that is fulfilled electronic configuration. Fulfilled electronic configuration. So that even though here lowest energy level is having only 1 electron, we are filling the electrons first in the higher energy level, because here 3D is getting the some extra stability by having fulfilled electronic configuration. So here number of exchanges n minus 1 with upward direction plus sigma n minus 1 with the downward direction. So here 5 electrons with upward direction plus 5 electrons with downward direction. So here summation of 4 means that is equal to, and here also summation of 4 that is equal to 10 totally 20 exchanges are possible. Means here one electron exchange with another electron, likewise so that these exchanges are possible. Because of these exchanges this is going to lose energy. So we already know energy is inversely proportional to stability. Okay, energy decreases, stability increases. Okay, thank you. One more last video is there, that is about nodes. So with that our atomic structure chapter is finishes. Then after I am going to review total on the atomic structure in bi language, that is Telugu and English. Okay, thank you.